Hi everyone, I am Whitroy. Today I invited electrical tutor Mark and apprentice Sarah to talk about NZS 3008. It is all about how to select the right cable for electrical installation. I hope you enjoy this type of study.
All right, Sarah. Today we're going to take our time and go through NZS 3008 properly. No rushing.
Yeah, good, because I feel like I kind of know bits of it, but not really the full picture.
That's exactly where most people are. This standard is not just tables. It's really about understanding how cables behave.
Okay, so why we choose a cable, not just what size.
Exactly. The scope of the standard is about selecting cables for low voltage installations, so up to 1000 volts.
So basically everything we normally deal with on site.
Yes, houses, buildings, workshops, most installations in New Zealand.
All right, so what's the main idea behind it?
The main idea is simple but very important. You must choose a cable that is safe and works properly under all conditions.
Sounds simple, but I guess it's not that simple.
Exactly, because safe depends on a few different things. So let's start with the big picture. When selecting a cable, we check three main things.
Okay, 3 things.
Current carrying capacity, voltage drop, and short circuit.
Right, I've heard those before.
Good. And here's the key idea. The cable must pass all 3.
Not just one.
Exactly. This is where people make mistakes. They check one and stop.
Okay, so where do we start?
We always start with current carrying capacity.
That's like how much current the cable can handle.
Yes, think of it as how much heat the cable can safely deal with.
Heat again.
Everything comes back to heat.
Right.
When current flows through a cable, it produces heat.
Because of resistance.
Exactly. And if the cable gets too hot, the insulation gets damaged.
And then it becomes unsafe.
Correct.
So first step is to find how much current the load needs.
Yes, that's your design current.
Then we pick a breaker.
Yes, the protection device.
And then the cable must be able to carry at least that much current.
Exactly.
But I always see those tables. Why can't I just pick from there?
Good question. Let me ask you this. What do those tables assume?
Maybe normal conditions?
Yes, ideal conditions.
So not too hot, not grouped, not in insulation.
Exactly.
But real life is never like that.
Correct.
So that means the table values are kind of optimistic.
That's a good way to think about it.
So then we reduce them.
Yes, we apply derating factors.
Okay, this part always confuses me.
Let's slow it down. Derating just means reducing the cable's current capacity because conditions are worse.
Can you give me a simple example?
Sure, imagine one cable in open air.
Easy cooling.
Now imagine 5 cables bundled together.
Oh, they heat each other.
Exactly. So each cable carries less current safely.
So grouping reduces current capacity.
Yes.
So what about insulation?
Insulation traps heat.
So heat can't escape.
Correct. So current capacity drops again.
And temperature.
Higher ambient temperature means less cooling.
So again, lower capacity.
Exactly.
So basically, everything that makes it hotter reduces capacity.
Perfect.
So after applying all these factors, we get the real current capacity.
Yes, and then we choose a cable size that meets that.
Okay, so that's current sorted.
Good. Now we move to voltage drop.
Right. This one I kind of understand, but I'm not confident.
That's fine. Let's build it slowly. Voltage drop means the voltage at the load is lower than the supply.
Because some voltage is lost in the cable.
Exactly.
So what causes that loss?
Resistance and impedance of the cable.
So longer cable means more resistance.
Yes.
And more current means more voltage drop.
Exactly.
So both length and current matter.
Yes, those are the big ones.
Why is voltage drop a problem though?
Think about a motor.
Okay.
What happens if the voltage is too low?
It might not start properly or it draws more current?
Exactly. It can overheat or fail.
So we need to keep voltage within limits.
Yes, and those limits are given in the wiring rules.
So how do we calculate voltage drop?
This is the exam part. First, find the current.
Same as before.
Second, find the cable length.
From supply to load?
Third, get the milliamps per amp per meter value.
From the table.
Then multiply. Voltage drop equals milliamps per amp per meter times current times length.
So it's actually quite simple.
Yes, once you see it that way.
And then compare with the allowed limit.
Correct.
And if it's too high, we increase cable size.
Yes.
So bigger cable means less resistance.
Exactly. So less voltage drop.
So even if current is okay, voltage drop can fail.
Yes, and that's a very common exam mistake.
Okay, that's clearer now.
Good. So what's next?
Short circuit. This is the one I know the least about.
That's okay. Keep it simple. Short circuit is a fault condition where a very high current flows.
Much higher than normal current.
Yes,
And that creates a lot of heat very quickly.
exactly.
So the cable must survive that heat.
Yes, until the breaker trips.
So this is about fault safety, not normal operation.
Correct.
So do we always calculate this?
Not always in simple jobs, but important for larger systems.
So if the cable is too small, it could be damaged during a fault.
Exactly.
Okay, that makes sense.
Now, the last part, just briefly, is economic selection.
Cost.
Yes,
So small cable is cheaper up front,
but wastes more energy over time.
and big cable costs more but is more efficient.
Exactly.
So engineers might choose a bigger cable for long-term savings.
Yes,
But for exams, we focus more on safety.
correct.
All right, let me try to summarize everything.
Go for it.
So first, we check current carrying capacity using tables, then apply derating factors, then check voltage drop using the formula, then check short circuit if needed, and maybe consider cost.
That's an excellent summary.
And the final cable size must pass all checks.
Exactly.
I think before I was just jumping around, now it feels more structured.
That's the goal.
Yeah, like everything links together.
It does. Current, heat, voltage, faults, it's all connected.
Thanks, Mark. This actually helped a lot.
No worries. Next step is practice questions.
Yeah, I think I need that to lock it in.
You will. Catch you next time.
See ya.